Okay, we are recording now. All right, so this is going to be our first lecture for the second half of Math 2010. So I saw you guys the first day of classes, and then I'm seeing you now. I hope your first half with the calculus went well. You guys are done with your exam one, and we are now on to the second half, which is going to be about matrices and matrix algebra. So um, before I get into the lecture, let me tell you guys a little bit about myself. The first day was, you guys just saw me, and then you guys didn't really find out who I am in detail. So let me take this opportunity to just say a couple of words. I am with RPI for the last close to 4.5 years now. I teach classes in the ECSE department. A lot of those classes are freshman, sophomore level, but I also teach some junior, senior level classes. My main responsibilities include the teaching. I'm not heavily involved in the research side of things, but that's where my passion lies in teaching. And I want you guys to uh, um, feel that you can talk to me, ask me questions, approach me, um, so that we both can learn this material. This is the first time I'm teaching this class. I'm not sure if I'll ever teach it again. So as I'm doing this, the first class in a math department, I'm hoping to learn how things work in other departments, and also learn from you. Having said that, I see a lot of names over here from ECSE. So those students may know me already. But for those of you who are getting to know me for the first time, I thought that that was a appropriate introduction. By academic training, I'm an electrical engineer. So if you hear currents, voltages, resistors, and so on from me, that's occupational hazard. Um, all right, so that's for my introduction. Now, office hours. My office hours are going to be Wednesday. Let me just write it over here. I hope you guys can see the slides that I'm writing on. These slides, by the way, I've uploaded to Piazza as well. So if you want to grab a copy from Piazza and write on top of these slides, if you have an iPad, that'll work really well. So you can do that if you have that slide over there. Slides are there. All right, so let me just write down my office hours here. Wednesday, 2 to 4 p.m. Eastern time, of course. And it's going to be on my WebEx personal room. All you have to do is search for my RCS, which is Hamim 2. And I've also updated this on Piazza. So you can look at my staff information on Piazza. There's a question in the chat box asking about the slides being posted on LMS. I have not posted the slides on LMS for this one, but if you really like them on LMS, then I can post it. I'm not a LMS user. I mainly use Piazza as a one-stop shop. But if you like it on LMS, just type that into the chat box, and I can post the same set of slides on LMS as well. I find Piazza to be a platform where material is organized in a good fashion. That's why I tend to use that for all my classes for making the material available. But if you want it on LMS, just let me know, and you can let me know during class or after class. All right, so Piazza. All right, so what is the best way to reach me? The best way to reach me nowadays is not email, it is WebEx Teams. So I use WebEx Teams. to communicate, that's the best way to reach me. Again, you're using the same RCS ID to find my team's contact. Okay, let's see. Questions up so far? Office hours, where are the office hours? What is the best way to contact? Okay. Now, this is the usual thing that I do. I post the slides ahead of time so that you can get a copy from Piazza. And then I write on them while we do the lecture. And then I'll post the written slides again. So I'll update the PDF on Piazza after we get done with class. So you'll have if you want the copy before the lecture, then you have to grab it before the lecture because I'm going to update that file after the lecture. And I've sort of changed a bit of organization on Piazza. I've made a new section for the second half of 2010. Okay, so let's try to look at the main problem that we are going to be solving. AX equals B. That's the problem that we are solving. And A is a matrix. We are going to call that a coefficient matrix. And it has certain number of rows and columns depending on how many equations you have, linear equations you have in your system. X is a column vector of unknowns. And then on the right hand side, you have B, which is also a column vector, but now we have these as known quantities. So you have A, which is known matrix, X, which is a unknown vector, B is a known vector, right? But if this was just straight up algebra and you had to solve for X, right? That's what we usually do. We solve for X. That's like our tagline. Math classes, we solve for X. So how would you solve for X? Well, you would just say X equals B divided by A, right? But that would work if those were simply variables. But it's not going to work because now we are representing a system of equations with A, X, and B. So instead, we'll have to find different ways to solve for X, which is not one unknown, by the way. It's a bunch of unknowns, right? So it'll have finite number of unknowns, 2, 3, n, any finite number. So that's going to be our goal, to solve for the vector of unknowns, X. What happened here? I think I'm not able to. Oh my gosh. Okay. All right, the slides got frozen for a little bit. Sorry about that. Let's continue. So that's what we are trying to do. And we are going to try to learn different ways to solve for that X. One technique that we are going to look at today is called gauss-jordan elimination, or we'll also look at Gauss elimination. Okay, I'm going to be strictly following the textbook Introduction to Linear Algebra, 5th edition by Johnson, Riess, and Arnold. You can find this as an e-textbook online. There are PDF copies available, so you can grab those. And if you are finding it difficult to grab a copy, you can either purchase it from the bookstore, Amazon, get it from wherever. If you need additional help, you can contact me as well. Today, what we are going to be focusing on sections 1.1 and 1.2 from the textbook. So let's talk about what is matrix algebra and what are we doing here realistically. Realistically, your problems, whatever problems you have that can be mathematically expressed, depend on many variables that are input variables, not just a single input. So for example, if you have a circuit, then a lot of things are going to contribute to a current at some node or voltage across an element. The circuit configuration, the value of resistors. So there are going to be several variables at play. And we'll take a look at some examples at the end over here. But the point is, many inputs are going to contribute to your problems. It's not just going to be one single input. You are going to have many input variables. So that's point number one. And that's real. That's realistically speaking. Next, your output variables, whatever you want to measure or observe or you're interested in, those output variables can be expressed as a function of several input variables. So for example, we said we are talking about a current or voltage example, current at a particular current through a particular circuit element or voltage across a particular circuit element. Those could be your output variables, and you could express that as a function of several input variables, maybe some resistors, for example. So output variables, there could be one, there could be many. Output variables depend on several input variables, and they will be connected with a function. What do we usually call that? We call that a input-output relationship, right? Now, if these are functions, then you know several functions, and the simplest functions of all are going to be linear, right? So many variables, outputs and inputs connected by functions, and those functions, the simplest functions of all, are linear, a straight line. So let's talk about linear and nonlinear in a little bit. But before that, let's take some examples, because math, in my opinion, once you start associating things in the real world, math will become more and more attractive. So let's take a look at some examples here. These are three that came to my mind. There are many, many, many examples that you could add on to this list where your output variables can be expressed as a linear function of several input variables. Some of them are: profit to some manufacturer depends on a few input variables. Cost of materials is one input variable. Labor, transportation, overhead. So all of those are inputs to the variable. So let me just say, if I say input, these are all inputs, right? That input 1, input 2, input 3, input 4. And all of those will dictate what the profit is going to be. And maybe the profit, your output variable, is a linear combination of all these other input variables. Profit depends 20% on cost of materials, 20% on labor, and so on. So that's one example where you are able to express this as a linear function. You are able to express problems as a linear function, a linear equation. And for all the electrical engineers in the class or computer systems engineers, in fact, if you have taken physics in high school, and you will get this. Currents or voltages in a circuit will depend on impedance of circuit elements. We have three laws that help us write those equations: Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. So if you have taken a circuits class, then you have mastered these three laws. You have understood and applied those three laws. What do you get? You get a linear combination. You are expressing currents and voltages. Those are your output variables. You are expressing them as linear functions of impedances of circuit elements. That's exactly what we are doing over there. Next, estimating flow of traffic through a network of one-way streets. And I want to sort of go deeper in this and actually develop the linear function for estimating the flow of traffic. So if you have a bunch of one-way streets, how can you estimate the flow of traffic? Now, to elaborate more on this, I have a network traffic analysis problem in front of you. So assume that these are all one-way streets, and on top of each arrow or arc, you have the flow that is expressed in vehicles per hour, right? So you have, if I zoom in over here, you have 800 vehicles per hour entering this particular junction A, and then X1 is the flow, vehicles per hour, that are exiting A to B and exiting A to junction F is X5, right? So this is your network of one-way streets. You can see that the arrows are going only in one direction from any two junctions. And you have certain numbers and some variables denoting the flow in vehicles per hour. Now you can use this particular network and analyze it. What are the unknowns? X1, X2, X3, X4, X5, X6, X7. There are 7 unknowns in this. And there are some given numbers as well. So how can you develop a system of linear equations given this particular network traffic? So you can start applying net traffic at any junction is going to equal 0. You can apply that to 4 of these junctions, A, B, F, and E. So if I look at A, let me see this. Maybe I can go points. Not, maybe 7 will do it. At junction A, if you apply that, what do you get? You get 800 comes in, X1 goes out, X5 goes out. So you've got one linear equation over there, X1 plus X5 equals 800. And similarly, you can develop for all the others, right? You can say at B, X1 comes in, X4 comes in, and then X2 goes out, 400 goes out. These are vehicles per hour. And then you can do the same thing at E, coming in, X7. Everything else is going out. X6 plus X4. And you can rearrange these equations to have all the unknowns on one side and a constant on the other side. You can do all of those things later on. I just want to develop a system of linear equations at this point. And at F, what do you have? You have things that are coming in are X6 and X5. Things going out are 400 and 600, right? So you've got 4 linear equations. And I just said linear. Why, how was I able to say that this is linear? Anyone? Use the chat box or your mic to answer the question. No power of 2. Yes. Specifically, or so no power of 2 or above, but then it could have just all power of 0 or -1, right? So it's not just 1. You're on the right track though. The variables X1, X5, all of the unknowns have a degree of 1. That's why you are able to call it a linear system. Now, if I zoom out here, I also had 2 more nodes, 2 more junctions at C and D. So you could also write those as well, right? I'm going to leave that exercise for you guys if you're interested, but I hope you get the idea. I'm sure you get the idea that you could write the 2 linear equations for junctions C and D as well over here. Now, with these, what did you develop? You have developed a system of linear equations. One of them is a linear equation. Bunch of them is a system of linear equations, or just a system of equations, which is expressing the network traffic that is expressed over here schematically. Now, of course, you are next going to ask the question, I should be able to solve for these unknowns, right? So that's the obvious next question. How do I solve for these 7 unknowns? You will also ask, do I have substitute stuff? Yes, substitute stuff, but we are going to learn systematic ways of solving this problem. So the first thing that we are going to do is we are going to take our system of linear equations and express it in a very methodical way, in a very natural symbolic language, which is provided to us by matrices. So we are going to translate this linear system of equations into a matrix representation. Then we will use some techniques. You have several options. You can use some techniques to solve for the unknowns. And then the last thing that we'll be left over with is talk about the solution. Talk about like the insight of the solution. What can you tell us more about the solution? Does it have a unique solution? Does it have infinite solutions? And so we'll do all of those things. Now, as far as we are talking about linear systems, this is also a linear problem, predicting the future, right? So for example, if you want to predict the demand for a certain product, or you want to predict the temperature on a certain day, depending on history, right? So depending on two things. One, the previously measured data or the previously predicted data. So if you want to use both those things to predict a future value, that particular problem can also be expressed as a linear function. And that's exactly what I'm doing over here. I'm expressing a future value, whatever that might be. This might be, give me one second. This equation looks like parameterization of a line going through 2 points. Yes, so it's a line, right? So but I could have several variables over here as well. So over here, I'm trying to predict a future value and I'm expressing that future value as a weighted sum. You see, I used alpha here and I used 1 minus alpha over here. Weighted sum of present and past values. So if I look at the present value is right here. No, sorry, present value that I'm predicting is right here. The tilde is suggesting a prediction, not actual. And yn is the actual. N is the time step. So whatever you are predicting for the future, time step n plus 1 could be expressed as a linear combination of actual at time step n, and this is predicted at time step n, right? So I had made some prediction earlier and it was actually this yn. So using those two values, I'm going to say, let me use 50% of my weight is going to be the actual time step and 50% is going to be my predicted at the previous step. And as I tweak that alpha, I am changing the weight that I have for history and actual, right? Predicted and actual. I can play around with those. And you can actually not just stop with y sub n, you can actually go back in the history, right? You can say y sub n minus 1, y sub n minus 2, and so on. Maybe you realistically want to have lower weights for the previous time step. So using all of that, predicted and actual data, you could actually predict the future. But the point here is, this is a linear problem. The variables over here have a degree of 1. Next, let's talk about the general case of a linear equation followed by its solution. A linear equation in n unknowns. You have n unknowns. Where are those unknowns? Those unknowns are here, x1, x2, x so on up to x sub n. Those are your n unknowns. And you have put it up as a linear combination of all those unknowns. But those unknowns have some weights, have some coefficients, have some known coefficients. Where are the known coefficients? We have those known coefficients as a1, a2, so on up to an. Those are your n known coefficients. Then on the right-hand side, for this particular linear equation, there's only just one equation here. On the right-hand side, you have what? You have a constant b, also known, right? So b is a known constant on the right-hand side. You can obviously rearrange the linear equation to express it in that particular form. x1, x2, xn, so on, all of those guys are variables, unknowns. There are n of them. Those are the only unknowns in our problem, in our linear equation. So that would be one linear equation. And we are able to call this a linear equation because of this reason. Each term has degree 1 in the variables. x1 raised to 1, x1 raised to 1, xn raised to 1. Some of these may be 0, right? So if you have x2 raised to 0, then you are really having a 1. That particular variable is not a factor, right? It's not mattering in that particular problem. So you could have those situations as well. So for example, you could have dependence on x1, x3, xn. Maybe there is no dependence on x2. That is also a linear equation. It just doesn't depend on x2. Next, if you have a linear equation, then you can start talking about what values of the unknowns will solve that, will make that equation satisfied. That's called a solution. A solution to the above equation, this is our linear equation here, is any sequence of S1, S2, so on up to Sn of numbers, such that if you had substituted x1 for x1, you substitute s1. For x2, you substitute s2. For xn, you substitute sn. And if that satisfies this linear equation, then you call that the solution of your linear equation. So the obvious next question is, how many solutions can you have? Can you have 0? Can you have 1? Can you have 2? Can you have 3? Can you have 4? Can you have infinite? That's the next question. And it turns out you can have only 3 possibilities. You can have no solution, you can have a unique solution, one solution, or you can have infinite number of solutions. I'm talking about a system of linear equations. For a system of linear equations, those will be your 3 possibilities. And we'll see why that is the case as we move on. So we have talked about a linear equation, how we are going to write it, what is the solution, and why are we calling it a linear equation. Whenever you guys have a question, please feel free to type that into the chat box. A quick exercise over here. Which of the following are linear? So this should be very, very easy to point out. So let's say we use red for bad and blue for good. Is the first equation linear? So this one was okay. This one was okay. This one was okay. But the problem is this. In the variables, you cannot have degree of 2 because over here in the variables, you have a degree of 2, x1 multiplied by x2. Because of that, this is not linear. Next, how about here? This should be easy. The second equation has a square root over x1, which makes it nonlinear. The third equation has a sine function. A sine function is not linear, and I hope you know that. Sine function is not linear. Exponential function is not linear. You also had a x to the minus 1. So that was not a linear equation. The last equation is going to be the only equation over here in which all the variables have a degree of 1, and that qualifies as a linear equation. So the top 3 are going to not be linear. Each term the key, each term should have degree 1 in the unknowns. This is a term. It has a degree of 2 in the unknowns. Moving ahead. Now let's do some graphical interpretation or geometric interpretation of linear equations. So I have two listed on this slide. I have a linear equation in 2 variables and a linear equation in 3 variables, both of them listed. And what I want to do is a simple exercise. What I just want to sketch this on a 2-dimensional plane. I've got x1 on the x-axis and I've got x2 on the vertical axis. I just want to sketch it, see what it looks like. So how can I do this? Maybe I can make x2 0. If I make x2 0, what do I get? Let's see. If I make x2 0, I get x1 to be what? 12. Yes. So I get x1 to be 12. And similarly, I can do the other case. What is that? X1 is 0. If I put x1 is 0, I get x2 as 8. Yes, 12 for x1. Then you have got. So my goal over here is to find out 2 points that are going to satisfy that equation. And once I have 2 points, I know that line. So one point, let's see here. One point was x1 was 0, x2 was 8. Somewhere there. And then the other point was x2 was 0. X2 is 0, x1 is 12. X2 is 0, x1 is 12, right there. And then when x1 is 0, x2 is 8, right there. Right. So you've got, let me draw arrows here to indicate what we are talking about. So that should do it. So I've got a red line, a red dot and a blue dot corresponding to the 2 points. Then all we do is connect those 2 points and we will be finding the equation of that line, right? So we have graphically represented those 2 points and you have an equation of the line. Let me also quickly write those 2 points out. This point was what? 0, 8, 0, 12. Yes, 12, 0. Oh my gosh. I want to write it as x1 followed by x2. 0, 8 here. Yeah, 12, 0. You got it. So those 2 points, I get a straight line, right? So each linear equation, when you draw it onto a 2-dimensional plane, you will have a line. And as you have more and more linear equations in 2 variables, you will have more and more lines. And the solution will be the point at which they intersect. And we'll have certain cases to look at. Now, if I did this for 3 variables, what would this look like? If for 2 variables you got a line, what would you get for 3 variables? A plane, exactly. Let's move on here. Now, here we have a system of linear equations. We are going to solve for the 2 unknowns. The 2 unknowns that we have are x1 and x2. Those are my 2 system of equations. Equation 1, equation 2, both combined, I have a system now. And the process for me to solve for the two unknowns, I'm going to use the method of substitution first, and I will use the method of elimination next. I'm hoping that most of you, if not all of you, have seen these two methods already. So let's see. In substitution, what are you doing? You are expressing, say, x2. You are expressing x2 as, say, 28 minus 4x1, and you are substituting this in equation 1. When you put this in equation 1, substitute in E1. What do you get? You get 2x1 plus 3 times 28 minus 4x1 equals 24, which implies what? 2x1. So you've got 2x1 from there, negative 12x1 there. So you got negative 10x1 equals 24. And then you have a minus there. And then you have 60 plus 18, 78. Right? Okay, so let's see. What does this imply? This implies that x, you guys keep checking this, checking my work. So 24 minus 78, you have got what, 54. Am I doing this right? 2x1 minus 12x1. I've got negative 10x1 there. 24, 60. Oh, this is not right. This should be 60 plus 24. That should be 84. Yeah. So now you've got x1 to be, okay, so now this simplifies. Good. X1 is 6. And if you put this into x2, you know that it should be 28 minus 24. So that should give you 4, right? So the solution over here is 6, 4. Meaning if you had sketched these two lines, you would get two lines and they would intersect at this particular point. And you have a unique solution in this case, just one solution. And similarly, you can do elimination as well. For elimination, what are you doing? Let's try to eliminate x1. The way you eliminate x1, it can be multiply equation 1 by 2. What do you get? You got 4x1 plus 6x2 plus equals 48. When you multiply equation 1 by 2, you get that. And then you can take this guy and subtract the next one. So you're eliminating x1 out of this. So what do you get? You get 5x2 equals 20. You get x2 equals 4, consistent with our previous result. And then you can substitute x2 back in any one of those equations to get x1. And it will come out to be 6, right? So that here we have eliminated x1 by doing this process. We multiplied the equation by 2 and then subtracted the second equation from the first equation to eliminate x1, solve for x2, substituted it back. You got x1 here. And again, the same point, right? It's the same 6, 4 is the solution, and it's a unique solution. So these were the two ideas that I'm sure you guys have looked at earlier. We are going to try to use some of the things that we do in substitution and elimination, but we are going to try to look for a systematic way to do it while solving a system of linear equations. Don't need to stop at 2. You could have 6, you could have 10 equations, right? And if you were trying to do this graphically, you would exactly get that. So let's see. For the first equation, I had a line, and that line, I remember, yes, it was passing through 12 comma 0 and 0 comma 8. This is my first equation. Already I had done that. So I'll just write those 2 points here. One was 0 comma 8 and the other was 12 comma 0. So if I make this guy say 2, right? 2, 4, 6, 8, 10. And if I make this guy, I think this is going nice, right? Let's see. If I go to, let's go 3, 3, 6, 9, 12, 15, 18, 21, 24, 27, and then 30, right? So I've just given it some grid to plot this on. I had 12 comma 0 and 0 comma 8. So I had a point here, and for 0 comma 8, I'm talking about something here. And if I sketch that straight line, no, close enough, I think. Yeah. So you've got that one line there. For the next one, what do you have? If x1 is 0, x2 is 28. And if x2 is 0, x1 is 7, right? So you've got those 2 points, 7 comma 0 and 0 comma 28. So 0, 28 will be somewhere here, and then 7, 0 will be somewhere here. And you can now start connecting these points like that. And the place that they meet should have been slightly 6 and 4, but I think we are okay. Unique solution, right? So I hope you get the idea there. So you can do this, right? This is what we are talking about in terms of a geometric interpretation, lines intersecting. Now, when you're talking about lines intersecting, if you had linear equations in 2 variables, right? 2 variables, then you can have one of these 3 possibilities, right? You could have lines that are coincident on top of each other. So this is coincident lines. These are parallel lines. And these are intersecting lines. So can you guys tell me, if you have coincident lines, how many solutions do you have to this? Infinite. Or infinitely many solutions. If you have parallel lines, how many solutions do you have? No solution. If you have intersecting lines, how many solutions do you have? Unique, one solution. Right? Can you guys think about when will you have this situation? The first case, coincident lines. Can you guys think of an example here? Let's just write an example here. X plus y equals 1. 2x plus 2y equals 2. 2 equations different by a factor. There you go, right? So these equations, they are exactly the same line. They are exactly the same equation. We just multiplied it by 2 and we wrote the second equation. So that's a possibility to that's where you get lines that are on top of each other, and every point on this line is a solution. So you got infinitely many solutions. Okay, how about parallel lines? For parallel lines, let me give you guys a scenario. Let us say that the equation for this guy is x2 equals mx1 plus b1, right? I'm just putting it same slope. That's right. So you've got this as one equation. What is the equation of the other guy? X2, same slope, different y-intercept, right? So if you have something like this with the same slope because of the same m, you have got parallel lines, which means they never intersect, so no solution. And unique solution, you just saw an example, right? 1 point, one solution. Let me ask you guys the next question. Two variables, you've got these three cases. What about the number of equations? How many equations are we talking about? Number of linear equations in the system. Two equations, why stop at two? So you could have any number of equations, right? Some of them may be coincident. Some of them may be zero. So you have to stop at two. What if you have a third equation? What if you have something like this? Parallel, parallel, this. What if you have this? No, Sunny, hold up. So what if you have this? Can you have something like this, where you have three equations and you have, these are two solutions, but would this qualify as a system of equations? It would satisfy as a system of equations, but this is inconsistent solution. Inconsistent. Why is that? Parallel lines means no solutions, but there are two intercepts. Yes. So you have got one line here. With this line, you could have found this point. That would have been solution. Fine. However, when you're trying to solve three equations, then you are really trying to find out one point where all these three meet, right? 1 point, but you don't have 1 point, you have 2 points. So this is inconsistent solution, right? You guys see that? So we are talking about two equations here. When you put in a third equation, then you may have inconsistent solutions. However, if you have something like this, what's going on over here? You have one line that is coincident, right? Like there are many lines on top of this. This is the coincident case. And there is another equation here which is cutting across. Does this have a consistent solution? Why not? It has a consistent solution, right? This is the only point which satisfies all the coincident lines drawn in black and the red line. So think about it like this. You have x. So this is this for this case, you have x plus y equals 1, 2x plus 2y equals 1, and then you have some other line, which is this. So there is one unique solution over here for all these problems, for these equations. What I'm trying to tell you is this: when you have more than two equations, then you may get inconsistent solutions, which is no solution at all, or you may get a unique solution. Can I see that? All right. So now let's add to this. I have many equations in my system, right? I have many equations in my system, but they're all coincident. What now? I am not stopping at two equations, 3, 4, 5. And I have many equations like that. Just keep different factors, more and more multiples, infinite solutions. So you see this, the number of linear equations in the system doesn't matter, right? So if you have 3 equations, 4 equations, 5 equations, you will still have an inconsistent solution, or you may have unique solution, or you may have infinite solutions. So the number of linear equations is not limiting your 3 cases. You still have 3 cases, but instead of, we are just adding one more terminology here, which is inconsistent solution, which is no solution at all. That is also a possibility. All right. Now let's talk about 3 variables. Clearly we said if you have 2 variables, then you have lines. When you move on to a 3 variable, then you have a plane, right? So a graphical interpretation of this particular linear equation here, a1x1, a2x2, a3x3, sum them up, you have a known constant on the right hand side, which is b. So when you sketch it out in 3D, you get a plane. And let us suppose you wanted to just do some simple things with this. Let us say we have x1 over here. Let's say we have x1 over here, x2 over here, and x3 over here. I just want to find out these points, right? Where is the plane intersecting the line? So what can you guys tell me about those points? In blue, all right, fine. So what is this point? And that, right? That's what we are trying to find out. So set the other variables to 0, right? So if you wanted x1, you would set x2 to 0, x3 to 0, and you would get x1 as b divided by a1, right? That would be the point where that plane intersects the x1 axis. Similarly, you can do the x2 and x3. So you've got what? Over here, you have got 0, b divided by a2, 0. And then over here, you've got what? 0, 0, b divided by a3. Okay. So one, said the other way. Yeah. So one linear equation in 3 variables, you've got a plane. Now let's start considering a system of equations. When you start considering a system of equations, in this case, we are looking at a 2 by 3 system. What does 2 mean? What does 3 mean? 2 means the number of equations. 3 means the unknowns, x1, x2, x3, x1, x2, x3. So you've got 2 equations, or think of it like 2 rows, and you've got 3 columns, x1, x2, x3, one for each. So this, of course, is plane 1, and this, of course, is plane 2. So when you sketch it out in 3D, you can have plane 1 over here, and you can have plane 2 over there. But you will only have each is a plane, right? So you've got plane 1, plane 2. There are 2 possibilities now. What are those 2 possibilities? The planes could be coincident, or they could intersect in a line, not a point, but in a line. So planes are coincident. What does that mean? That means that it has infinitely many solutions, infinite solutions. Or If they intersect in a line, right? So if they are going crisscross, they intersect on a line. There are only two of them. Then you have what? You have infinitely many points because it's a line now. However, if the planes are parallel the way that is shown, then you don't have any solution. So again, you have got two possibilities here, which is infinitely many solutions or no solution at all. So why is this case important? This case is important because if earlier when we were asking this question, number of linear equations in the system, if you had many equations in the system, you still have three cases. Oh, okay. Sorry to hear that, Melanie. But if you have the number of equations are less than the number of unknowns, then you have two possibilities, infinitely many solution or no solution at all. You do not have the case of unique solution because the number of equations are not enough to find that. You guys see that? All right, let's see. Now we have a general 3 by 3 system. What is a general 3 by 3 system? Three equations, three unknowns. In that case, you have got three planes. Those three planes will give you those three cases. The first case is infinitely many solutions. So this is the three planes are in such a way that you are getting a line that is at the intersection point. So three planes are intersecting in a line. And if that is the case, you have infinitely many solutions because there are infinite points on that line. In the second case, the three planes are parallel to each other. They don't meet, no solution. In the third case, the planes are such that they intersect on one point. That is a unique solution. So I hope now you start seeing a pattern. When we were talking about two variables, you had those three cases, infinitely many solutions, no solution, and unique solution. When you're talking about a three variable situation, three unknowns, again, you have those three possibilities, infinitely many solutions, no solutions, and unique solutions. In fact, when you expand this to a general m by n system, m equations, n unknowns, you still have those three possibilities, infinitely many solutions, no solutions, unique solution. Having said that, let me ask you guys this. If you have a system of equations, can you have five solutions to that system of equation? Any system of linear equations, can you have five solutions? What happened here? The question is simple. Can I have five solutions? Can we have five solutions to a system of linear equations? No, no, no. They all need to intersect in one point. That would qualify as a solution. So think about this. If it's a system of linear equations, you will only have three possibilities, infinitely many solutions, no solutions, and a unique solution. When we were talking about two variables, we had coincident lines, parallel lines, or intersecting lines. Three possibilities. When we had planes, same three possibilities, infinitely many solutions, no solutions, unique solution. So you're talking about two variables, three possibilities, three variables, three possibilities, any variables, three possibilities, infinitely many solutions, no solutions, unique solution. Now let's answer this. can we have 5 solutions to a system of linear equations? No. You can have 0, you can have 1, you can have infinite. What if the two planes are parallel and one is perpendicular? That is inconsistent. Yes. That is inconsistent because you want all the planes to be intersecting at a point for a unique solution, right? So it has to satisfy all of them. It cannot satisfy just 2 of them. It has to satisfy all of them. You see that when you have 2 planes that are parallel, right away, there is no solution between them, right? So that would be no solution. That's inconsistent system of equations. All right, questions here. These are the only 3 possibilities. No solution, one solution, unique solution, or infinite solutions. All right, let's move on. Now let's start to talk about a general m by n system of linear equations. What is m? M is the number of rows. So look at how we have talked about this. A11, A12, A1n, right? So these are my n variables, the n unknowns, x1, x2, xn. Those are my n unknowns. The coefficients are a's, a11, a12, so on up to a1n. So the first, that's your first equation, second equation, and so on up to the mth equation here. The coefficients are different. The unknowns are the same, x1, x2, x3, and so on. The constant on the right hand side, b's, are known, but they're different, b1, b2, b3, and so on. You can see that. So this is going to be your general m by n system, m rows and n columns. M rows, m equations, n columns, n unknowns. Still, you have 3 possibilities for the solution sets. What are those 3 possibilities? We have sort of talked about this many times now. Infinitely many solutions. Next, unique solution. Next, no solution. So for any system, you have those 3 possibilities. All right. Now quickly summarize the system of linear equations. A system of linear equations has either no solution, exactly one solution, which is called as unique solution, or infinitely many solutions. For example, coincident lines. Next, let's talk about the terminology that I've already used. Let me formally define that. The difference between a consistent system and an inconsistent system. A system is said to be consistent if it has one solution, if it had at least one solution, right? So this includes 2 possibilities, one solution and infinitely many solutions. Those are consistent systems. Otherwise, it is going to be an inconsistent system. So when you have those parallel lines or parallel planes, those are all inconsistent systems. No solution at all. We'll talk more about consistent and inconsistent systems in the next lecture as well. All right, questions so far? All right, let's move on. Now let's talk about matrices. We were here to talk about matrix algebra. We just don't want to spend all our time on talking about linear equations. So matrices, what are matrices? It's a language, it's a natural symbolic language to describe linear systems. So we have a linear system of equations. We are going to try to describe that using a symbolic language, and we are calling that matrices. In fact, it's not just, we are not going to stop there. We are in fact going to later lay down a framework to solve for linear problems, such as a least squares problem. So matrices not just give us the ability to describe them, but also to solve those linear problems, such as a least squares problem. Today, we are not interested in solving those. Let's first start with expressing the linear system using matrices. So the general m by n matrix, you remember the general m by n situation here? Those are the m equations that we are talking about. How do you express this in a matrix form? Matrix is a rectangular array of numbers. As simple as that. These are rectangular array of numbers. What do they have? They have the coefficients, right? These are all the coefficients that went along with our unknowns, a11, a12, and so on. Where did we see them before? We saw them here, a12, a11, a12, and so on, right? All of them. So all of those coefficients put together in one rectangular array is your matrix A. Now the question is, what should I call this matrix A? What would be a good name for this matrix A? It's called the coefficient matrix. And the reason is simple. It is an array of numbers that are representing coefficients in my linear system of equations. So A is my matrix. Let us quickly look at the number of rows, number of columns, and what does A sub ij indicate in this matrix? What is the number of rows? Anyone? 1, 2, 3, 4, so on up to m, right? So you've got m rows. What is the number of columns? 1, 2, 3, 4, n. N columns. Now the next question is, what does A sub ij indicate? So for example, what does AM2 indicate or A22 indicate? Any ij, what does that indicate? It indicates the number present in ith row and jth column. You see this? Ith row and jth column, Aij indicates the number present in that row and that column. You see? First row, first column, first row, second column, first row, nth column, mth row, second column, second row, nth column, mth row, nth column. You see that? So it's the number that is present in that ith row and jth column. We also represent the coefficient matrix not just as the rectangular array of numbers, but if you wanted to represent that in a very compact fashion, then you can represent it like this. This is representing a matrix with values A sub ij. You can see that? So let me also connect this. When you say m by n system of equations, you're talking about the number of rows first, followed by the number of columns. M first and second, right? So m is 1, 2, 3, and so on up to m. N is 1, 2, 3, so on up to n. Questions here? This is just the coefficient matrix, by the way. We have not put in the variables, the x's, or the constant. We have not put that in yet. We have just talked about the coefficient matrix. Now let me do this example. I have a 3 by 3 system here, 3 equations, 3 unknowns. And I'm going to try to represent this in the matrix form. And I'm only going for coefficient matrix first, and then I'm going to actually make that into an augmented matrix. An augmented matrix is simply coefficient matrix followed by the constants in the system. So let me talk about that here. So I have coefficients of the first row, 1, 2, 1. Coefficients of the second row, 2, -1, -1. Coefficients of the third row, 1, 1, 1. Right? You see, 1, 2, 1. That's coefficients of the first row. Then 2, -1, -1. Coefficients of the second row, 1, 1, 1. Coefficients of the third row. That would have been my coefficient matrix. If I close it out, this is my coefficient matrix. What is the problem with this? Does this represent this? It doesn't, because it is missing the information of the constants, right? So if you want to really display all the information about the system of equations, then you also need to write in the 4, 1, and a 0. So the question is, where are you going to do that? Well, you're going to pad that over here. 4, 1, 0. This is called the augmented matrix. With the coefficients, it was just the coefficient matrix. With the coefficients and the constants, it's the augmented matrix. And the augmented matrix, usually you use letter B for that. Coefficient matrix, you use A for that. So this now has all the information. You have the coefficients of the unknowns equals 4. Coefficients of the unknowns equals 1. Coefficients of the unknowns equals 0. So if I were asked to go back to this now with the augmented matrix, I would be able to do that. Questions here? How do you take a system of linear equations and represent them using an augmented matrix? And a helpful question is, why didn't we stop at coefficient matrix? The answer to that obviously is that it did not have all the information. If you wanted all the information about that system of equations, then we had to also include that column right here. Now, sometimes in some textbooks, you will see a vertical line separating the coefficient and the constants. But in our textbook, there's no vertical line that is separating the coefficient matrix with our constant vector. So you'll have to pick that up with context, right? Like you need to sort of clearly talk about what type of matrix is it. Is it an augmented matrix or is it coefficient matrix? So sometimes you'll find a line, sometimes you don't. All right, questions? Going once, twice. All right. So here, we did that for the 3 by 3 case, and over here, I have done that for the general m by n. M is what? Number of rows. N is what? Number of columns. If you look at the system of equations, then m is the number of equations. N is the number of unknowns. And I've represented this linear system of equations using a coefficient matrix and an augmented matrix. The coefficient matrix is A for this system, which is represented over here, and it contains that coefficients. The A's, the coefficients everywhere over here, right? So you have got A11 and A12 and so on up to AMN, right? It is what? Size is what? M by N, right? Let me write it in that. M rows, N columns for the coefficient matrix. Now for the same set of linear equations, that's my system of linear equations, I can write the augmented matrix B. And notice over here, the coefficient matrix is simply written as coefficient matrix, and you are padding B vector, right? This is vector, column vector of constants on the right hand side. You're simply padding that onto it, which is right here, right? So you see this B is right there, which in our equation was right here. What would be the size of the augmented matrix? Anyone? What is the size of the augmented matrix here? You are close, Sunny. How many rows does it have? Look at it again. How many rows does it have? You're right with the number of columns. M, right. So over here you have got M rows. Here you have got M rows. Over here you have got N columns. But over here you have got all these are fine. N columns, right? But you have padded on one. So the size over here would be M by N plus 1. M rows, N plus 1 columns for the augmented matrix. They are color coded. So hopefully you see that coefficient matrix is here in red, and then the blue one is the augmented matrix for the same set of linear equations. This is the general case. All right. So questions here? Okay. Now let's talk about elementary operations. This is going to be essentially our first attempt at solving a general M by N system of equations. What is the difference between an equation and a system of linear equations? What's the difference between linear equation and a system of linear equations? A linear equation is one equation. A system of linear equation is many equations that are representing the system that you are observing, right? So many equations, you've got a system. You've got one equation, you've got a linear equation, or just one equation. So we are talking about solving a system of linear equations. So the obvious next question is, how many equations are there? M equations are there. How many unknowns are there? N unknowns are there, right? There are two steps that are involved. One is reducing the system, reduction of the system, which also means that you are trying to eliminate the variables. The same thing that we did earlier in our lecture. We were trying to eliminate not the substitution method, but the elimination method. We eliminated x1, then we found x2, we substituted back in one of our equations, and we got the value of x1 from it, right? But we are going to need a systematic approach to reducing the system, and we are going to work at that. Once you have that reduced system, then you can describe the set of solutions, right? Is it infinitely many solutions? Is it unique? Is it no solution? You can talk about that once you have that reduced system. So here are the steps that we are going to follow. One, you have the system of equation. Then we are going to try to reduce the system or simplify the system of equations. And then we are going to get the solution and then talk about the solution or describe the solution. So the goal is to simplify the given system of equations by eliminating the unknowns. Just as we did for the equations earlier, we had two equations that we did this for. Now, it is essential that the reduced system of equations has the same set of solutions as the original, right? So the original has some solution. When you reduce the system, you simplify it. You don't change the solution. The solution is still going to be the same solution. Two systems of linear equations with n unknowns are said to be equivalent if they have the same set of solutions. In other words, the original system of equations that you started off with, you simplified it, you got a reduced system, simplified system. They are going to be equivalent if they have the same set of solutions. We are going to use three operations called as elementary operations that can be used for reducing the system. And we are talking still in terms of equations. We have not started talking about this in the context of matrices. We are still talking about it as equations. So we are going to look at three operations that you can do to equations while keeping them equivalent, right? So you have a big problem, you're trying to simplify the problem. The big problem is original set of equations. You're trying to simplify that, reduce that, so that finding the solution is easier. And while you do that, the solutions should not change. And so solutions will not change if you do these three operations. What are those three operations? I've listed them over here. That's theorem 1 in the textbooks. First thing, interchange two equations. If you interchange two equations, you don't change the solution, right? If I change equation I with equation J, it is simply swapping the two equations. I'm not changing the system of equations if I just change the interchange the equations, right? I simply change the ith and jth equations. System is the same. I've not reduced it, but the system is the same. So I can interchange equations. I can make equation 2, equation 1, equation 1, equation 2, right? Interchange them. I can also multiply an equation with a non-zero scalar. Where did we do this before? We have done this before, right here. You see this? We took equation 1, we multiplied it by 2. And we did that because we could quickly eliminate x1 in this case. So multiplying an equation with a scalar all throughout, the coefficients get adjusted as well as the constant gets multiplied by the same factor. And if you do that, you simply have the same equation, the same line in this case. So that will not affect your system of equations. So that's second condition over here. You multiply any equation with k, you don't change anything. You can do that in the process of reduction. The ith equation is multiplied by a non-zero scalar and you will be fine. Next, add a constant multiple of one equation to another. You can take equation I, add k times equation j, and substitute in place of equation I. So this is like saying something like this. An example would be E1 equals E1 plus 2 times E2. You are replacing equation 1 with equation 1 plus 2 is your scalar times equation 2. You could do this, and we did right here. You see, oh, we subtracted, right? So in our case, the scalar was not plus 2, it was minus 2. So equation 1, 2 times equation 2 and equation 1. When we add, you're doing this to what? To eliminate the unknowns. You can do this as well. So those three are the operations that you can do as elementary operations while keeping the equations equivalent, the system of equations equivalent. Those are the three. Key is we are trying to keep the system equivalent, same as the original. And you do these steps to reduce it, right? Those are the three things that you could do for the equations. So let's try to quickly do this example here. We have two equations. I'll call them E1 and E2. I'm going to try to use elementary operations to solve the system. So what are the elementary operations that I could do? To save time, let me just work through it. If I do E2 plus E1, I will be able to get rid of that x1, right? So if I do e2 plus e1, what do I get? I get the first one remains as is, right? The first equation remains as is, but the second equation has changed. The second equation has now become 3x2 equals 9, right? Do you see that? That's the first elementary operation that I did. I just added e2 and e1. I'm rewriting both the equations as I do these linear operations, elementary operations. The next operation that I'm going to carry out is I will divide e2 by 3 to get rid of the 3 so that I know x2 is going to work out to be 3, right? So if I do that, I'm not changing the first one, but I've changed the second one. The last thing that I'm going to do as elementary operation is e1 minus e2. Now, when I do e1 minus e2, I don't change e2, I change e1. What am I changing e1? I've got what? x2 gets out, I will be left with x1. And 5 minus 3, I get 2 here. And this remains as is. So you see, these are the 3 elementary operations that we did. And while we did these 3 operations, we wrote the 2 equations after we did each of those operations. We first eliminated x1, then we made sure that we get x2 by using a scalar of 3 divided by 3. And then we again used one of the elementary operations to eliminate x1, x2 from the first equation. So we have solved this using elementary operations, which are okay for equations. How many solutions does it have? This system of equation has unique solution, right? And the solution is right here. How did you get 3x2 equals 9? So you see, when I did e2 plus e1, I added this and this. So these two guys canceled out. This gave me 3x2 and this gave me 9. Yeah. All right. Now, if we can do that to those equations, they will have some corresponding meaning towards our matrices as well, right? So when we do this for equations, we call them elementary operations. But when we do this for matrices, and we are going to specifically target the augmented matrix over here, we are going to call those operations, those same operations, elementary row operations. So we are, instead of interchanging equations, we are interchanging rows. Instead of multiplying equations by a non-zero scalar, we are multiplying a row by a non-zero scalar. Instead of adding a constant multiplication of one equation, we are doing it for one row to another. So same thing, all we did is we did this. We translated equations to rows in the augmented matrix. Because we know the equations are really the rows in the augmented matrix. First row in the augmented matrix corresponds to the first equation, and so on. So if you do elementary operations for equations, those should translate exactly the same way for elementary row operations in the case of an augmented matrix, which is representing the same system of linear equations. So we've written down the same steps, except instead of talking about E's equations, we are talking about R's, rows. You can interchange rows in the augmented matrix. You can multiply any row in the augmented matrix with a non-zero scalar. You can multiply any row in the augmented matrix by a non-zero scalar k and add it to an ith row. Now, in terms of convention, let me just point this out. You are replacing Ri with this, by the way. You're not changing Rj, right? So when you do this, you are changing Ri. When you do this, you are changing Ri. When you do this, you are swapping Ri and Rj, right? Interchanging. So all we did is we took the same slide and instead of writing equations, we wrote rows. It's exactly the same. And instead of calling them elementary operations on equations, we are calling them elementary row operations that we are going to carry out on augmented matrix. Augmented matrix, by the way, has all the coefficients. It also has the constants. So we are building up to how do you solve a system of linear equations in a systematic manner, and we are going to call it the Gauss elimination, or we'll also look at Gauss-Jordan elimination method. We are laying the foundation to get there, right? All of these steps are going to help us do that. Now, row equivalent matrices. Row equivalent matrices. These are going to help us transform the augmented matrix to a simpler matrix, simpler system. Again, the problem is the same, right? Original system is too complex. I don't know the solution right away. So I'm going to simplify it using row operations or elementary row operations so that now I can quickly talk about the solution and then describe it. Now, while I go from a complex system of equations to a simpler set of equations, or the reduced system of equations, earlier I was doing elementary operations. Now I'm going to be doing for matrices row operations. And in both cases, I should not be changing the solution set. I should keep the original system and the reduced system equivalent. So whenever you're doing these three row operations, the ones that we listed over here, we are keeping the original system equivalent, row equivalent. So two matrices of the same size m by n, we are calling those two matrices B and C, are considered to be row equivalent if one can be obtained from the other by a sequence of elementary row operations. So you have B, you do some elementary row operations, you go to C. And if you do the math correctly, if you are not making any mistakes while you are doing the row operations, then they would be row equivalent. And we know what qualifies as elementary row operations. There are three of them. Interchange, multiply by scalar, and add to another row. So the system of linear equations you can solve with the following steps. One, start with the augmented matrix of the system, has the coefficients, has the right-hand side constants. Then use row operations to transform this augmented matrix to a row equivalent matrix C, which is hopefully going to be simpler. And then we are going to solve the simpler system of equation. So instead of solving complex augmented matrix B, we are trying to solve a simpler system. Now the question is, what is the simpler system, right? That's what we need to talk about. How do we know it's a simpler system? Where do we stop simplifying? Where do we stop with the elementary row operations? That's what we need to talk about next. So here we have an example here in which we are going to do some row operations to reduce the augmented matrix. So I'll go through this example here where I'll start with the augmented matrix. The augmented matrix is going to be what? For equation 1, I've got no x1 there, 2x2, 1x3, and then -2 for the right hand side constant. Remember, I'm not doing a coefficient matrix, I'm doing an augmented matrix here. Then for the next equation, I get the next row. 1. Then I've got 2, 4, -2, and 2. That is my augmented matrix. Now, how the row operations that I'm going to do over here, I have 3 of them. So let me start with this. I am going to do these row operations. Later, I am going to describe the formal process, like a step-by-step process that kind of does the same thing that I'm going to do over here. So I'm going to be essentially walking you guys through the Gauss-Jordan elimination process. So the first thing I'll do is here, in red, I will say, I'm going to swap row 3 with row 1. So when I swap row 3 with row 1, my augmented matrix becomes this. 2, 4, -2, 2, 3, 5, -5, and 1, 0, 2, 1, and -2. I have swapped row 3 and row 1, and the reason why I did that is because I'm essentially trying to do this. I am trying to make this into a reduced echelon form. And the reduced echelon form I'm going to try to go for is an identity matrix. I'm going to be doing row operations over here to make this part of my system into a identity matrix. That is what I'm going to try to reach. This is called a reduced echelon form. We'll get there. So the first thing that I did was what? You see the zeros are at the bottom. So I made the row 3 go down and I swapped it with row 1. And I want a 1 over here. So obviously I need to divide row 1 by 2 next. So after I do that, I will do row 1 divided by 2. Row 1 divided by 2 will change row 1. It will not change row 2 and row 3. So now I have what? 1, 2, -1, 1. The other remain as is. And the last one remains as is. Can I see that? All right. Now the next step is going to be what? You see, I want this to become a 0. How can I make this guy a 0? Well, I can take row 2 minus 3 times row 1, right? If I did row 2 minus 3 times row 1, I would have got a 0 over there. So essentially, here is the thing. First, you get your 1. Then you use that 1 to make the other 2 things in that same column go to a 0. This is already a 0, so you're good there. But you can use this one to make this into a 0. You're moving from left to right as you reduce this. So the second step I'm going to do is right here. I'm going to do row 2 minus 3 times row 1. If I do that, my row 1 doesn't change. My row 2 now becomes -1, -2, -2. And you guys can check my math later on if you're interested. I have checked it once, you can check it again. So I've got row 2 minus 3 times row 1. Remember, this is what I'm replacing row 2 with. So whatever I write ahead, that's what I'm changing. I'm changing row 2 only. Other 2 rows are the same. So I've got 1, 0, 0. My first column looks good. Now I need to change something about my second column. I wanted a 0 here, right? So let me try to do that next. I will do R1 minus R3. If I do R1 minus R3, I will make that into a 0, right? So let's do that. The sequence of steps that I'm taking is not unique, right? So you could use your own steps and get to the same answer. 0, 2, 1, and -2. I have simply changed row 1 with row 1 minus row 3. I've got that. Next, I want this to go to 0. If I want this to go to 0, I can multiply row 2 with 2 and add it to row 3. You see, when you do that, because of this 0, this doesn't change, right? That's why we made the zeros first over there. Let's see. R3 needs to change 2 times R2. 1, 0, -2, 3. R1 doesn't change. R2 doesn't change. R3 now changes. This becomes 0. This becomes 0. Now this becomes -3. Then this becomes -6. All these are augmented matrices, by the way. So we're done with that. At any stage, if you have any questions, please feel free to stop me there. I wanted a 1 here, right? So if I want a 1 here, I simply multiply the second row with, let me just do it over here. Also do this, right? Row 1, row 2. -1, row 2. I'm multiplying row 2 with -1. If I do that, I will get rid of this sign, and this sign. So I'm done with 1, 0, 0, 0, 1, 0. Now I'm going to work on this particular column. Next, so row 3, I will divide that by -3. Row 1 doesn't change. Row 2 doesn't change. Row 3 now becomes that 0, 0, 1. All right, now I need to do quickly. These two guys, I want them to be zeros now, right? If I want them to be zeros, I can, the first thing that I can do is change R2, and I will make R2 as 2 times, minus 2 times R3. So I made this guy a 1, then I'm using this one to make these guys a 0 here and here. Let me also write, so what do you get here after this? Row 1 doesn't change. Row 2 now changes. And row 3 doesn't change. Last, I need to eliminate this guy, make this into a 0. Changing row 1. This will be 1, 0, 0, 7. R1 plus 2 times R3. Row 2 doesn't change. Row 3 doesn't change. You can see that? So by doing all those row operations, I got this side of my matrix as an identity matrix. Nice. All right, so now when you look at this, try to write the equations now. What equations will you get now? 0x1 plus 0x2 plus x3 equals 2. That's exactly right. Yes. x1 plus 0x2 plus 0x3 equals 7. So x1 is 7. 0x1 plus x2 plus 0x3 equals -2. You've got the solution now, right? It's a unique one. You have got x1 equals 7. You have got x2 equals -2. And you've got x3 equals 2. A unique solution. So what we did, the process we followed is called gauss-jordan elimination method. We will make this into a formal process soon, but that's what we did. This particular form is also called a reduced echelon form. We will also talk about that soon. All right, questions about this example? I'm glad to hear that, Sunny. All right. So the next thing that we need to talk about is echelon form and the Gauss-Jordan elimination. We actually did Gauss-Jordan elimination, but we didn't formally talk about it because we need to have some terminology to reflect all these terms so that there is a system that can be made while you solve the system of linear equations. Because the question that should be troubling you is this: has the augmented matrix been simplified enough? How do you know when to stop? Well, we knew when to stop because I said I'm shooting for this, right? At the beginning itself. But how did I know I want to shoot for this? Why didn't I shoot for something else? For that, we need to talk about two forms: echelon form and reduced echelon form. So that's what we are going to answer next. Has the augmented matrix been simplified enough? So what is the general procedure for solving a system of linear equations? You start with the given system of equations. You obtain an augmented matrix from those system of equations using the row operations. You reduce it to a reduced matrix. In the reduced matrix, you get a reduced system of equations, which will directly lead you to the solution, right? By the way, over here, the reduced system of equations was what? X1 equals 7, X2 equals -2, X3 equals X3 equals 2. That was our reduced system of equations. And that was the solution, unique one. So, what are we going to be doing? We are going to be worrying about this to this process, right? This to this. How do you go and where do you stop? How much do you need to simplify? The system has been simplified as much as possible when it is in the reduced echelon form. So you stop simplifying your matrix when you reach the reduced echelon form. One such example of that was the identity matrix, which had ones in the diagonal and all the other elements were 0. So we need to shoot for a reduced echelon form. And if you go to the reduced echelon form, that elimination process is called the Gauss-Jordan elimination. And if you simply go to echelon form, that process is called Gauss elimination process. But if you leave things in the Gauss elimination process, then you will have a little bit of work to do in back substitution from the reduced system of equation to the solutions. So for example, if say, instead of shooting for one's identity matrix, what if I did this? What if I did all the row operations such that my augmented matrix, the coefficient matrix part of my augmented matrix became this? What would have happened in that case at the end? Suppose you have a 1 there, 1 there, 1 there. Well, you will have an equation for x3 and you get x3. That's good. And then you will get an equation in x2 and x3, and then you will have to back substitute that x3 to get x2. And then the first one will be an equation in x1 and x2 and x3, and then you will back substitute x2 and x3 to get x1, right? That is called Gauss elimination, right? So there is some work left at the end using the back substitution. Exactly, Sunny, you got it. So that's essentially the difference between an echelon form and a reduced echelon form. With the identity matrix, we went all the way down, reduced echelon form, the simplest possible, as much as possible. But Gauss elimination stops at echelon form. But there's a little bit of work left for that to happen. All right. What is echelon form? The first thing that I'll tell you is this: echelon form is not unique. You will have many echelon forms. So let's try to identify echelon forms. An m by n matrix B is in echelon form if it satisfies all these three conditions. The first condition says all the rows that consist entirely of zeros are grouped together at the bottom of the matrix. If you have all zeros in the equation, all zeros in the row, then you need to put that all the way at the bottom of the matrix in order for that matrix to be called in echelon form. For example, this. The zero row with all zeros is all the way at the bottom, all the way at the bottom, all the way at the bottom, right? And if you have many rows like that, you should put that all the way at the bottom of the matrix. That is one condition, the first one. Second, if every non-zero row, in every non-zero row, the first non-zero entry from left to right is a 1. Meaning, as you are going from left to right in the matrix, you should have a leading 1. Example, leading 1, leading 1, leading 1. You see that? The non-zero entry, the first non-zero entry was a 1 as you scanned from left to right. 1 there, 1 there, 1 there. Similarly, 1 there, 1 there, nothing there. That's fine. 1 there, 1 there, right? This applies for the rows that have a non-zero entry. If you have all zeros, then you just put it all the way at the bottom of the row matrix, right? So the leading, essentially leading ones, right? So you can think of the second condition as leading ones. The first condition can be like all zeros row, put it at the bottom. Next, the third statement is slightly complicated, but I will try to explain it in a easier manner. If the I plus 1 row contains non-zero entries, then the first non-zero entry in the column to the right of the first non-zero entry in the ith row. Essentially, what that means is, if you have a non-zero entry over here in the first row, in the second row, your non-zero entry should be to the right of this. You cannot have it here. You have to have to the right of this. And this essentially makes a staircase kind of a system, right? And even for this. So if you have any non-zero entries, for the ones below, you only have to have it to the right. You cannot have it, and it doesn't matter if you have it immediately right or 2 steps right, but they have to be to the right. These 3 conditions, if they are satisfied, then that particular matrix is called in echelon form. And clearly, it is not a unique form. So if you start with a particular augmented matrix and you get it to an echelon form, it's not unique. I can get it to 1 echelon form for the same starting point for the same original system, and you could get it into a different echelon form for the same system. They are different echelon forms. However, we both still have the same row equivalent matrices because the solution is the same if we do our math right. These are 4 of the 7 possible 3 by 3 matrices in the echelon forms. And the stars over here, the asterisks over here, can either be zeros or non-zero. And the example that we just saw earlier, I said 1, 1, 1, right? Like that was the echelon form. But you could have it in other forms as well. You just need to satisfy these 3 conditions. Let's try to let's try to identify how these matrices are in echelon form. The row with all zeros is put all the way at the bottom. That's good. We observe that, right? The first condition is met. Then we talk about the leading ones. Leading 1, leading 1, leading 1, leading 1. So that's good. Next, we talk about the staircase. Satisfies. So all three conditions have satisfied over here. All zeros go in the bottom row. Good. Leading ones. Good. The leading ones are moving right as we go down the matrix. Good. So A is in echelon form. Next, we can do the same thing for B. Well, in this case, the first condition doesn't matter because there is no row with all zeros over here. So we can ignore the first condition. How about the second condition for the ones? Leading one, leading one, leading one. Right? The first non-zero entry as we move left to right in each row is a 1. That's good. It satisfies. Next, we look at the staircase. Good. That is also satisfying. Can I see that? Those three conditions, if they are satisfied, the matrix is in echelon form. And if you stop at echelon form while you are simplifying your system of equations, then you would have done a Gauss elimination method. But with Gauss elimination method, you still have to write out the reduced system of equations, do some back substitution that will be left, and then you can talk about the solution. So if there is a 1 right below another 1, it is not in row echelon form. That's exactly correct, Dan. But I hope you're talking about only the leading ones, right? Because this could have been a 1. This could have been a 1 and you will be fine. The constraint that you are posing applies for the leading ones. You cannot have that any below the leading ones. But this is fine. This would have worked. All right. Questions here? All right. So echelon form is okay, but the problem with that is it is not unique. So we search for a unique reduced system of equations. And the unique reduced system of equations, for that to happen, you need to have your augmented matrix reduced all the way down to a reduced echelon form. And the way you get reduced echelon form is simply to add one more constraint to the echelon form. Just one more constraint. And what is that constraint? The constraint is a matrix that is in echelon form is also in reduced echelon form provided the first non-zero entry in any row is the only non-zero entry in its column. So if you look at the leading ones, all the other elements are zeros. You see that? Zeros here, zeros here, zeros here, zeros, zeros, zeros. So if you have a leading one, apart from the, it's a column detection now. Now you're looking at columns. If you have a leading one, apart from that leading one, which is the only non-zero, it should be the only non-zero entry, right? The only non-zero entry in that column. Because all the others should be 0. And this applies to the leading ones. Remember, we tried to do that example with Gauss-Jordan elimination. We shoot it for an identity matrix, right? That was this. It was the reduced echelon form, which is why looking at the solution was very quick. We were able to do that very easily. So you can do this. You can check whether the matrix is in echelon form first or not. And then you look at the columns to talk about whether it is reduced echelon form or not. By the way, if you start with a system of equations and you reduce it down all the way to a reduced echelon form, it will be unique. So all of us will have the same answer for the reduced echelon form. So let's try to do this particular classification. Let's check whether a matrix is in echelon form or not, or reduced echelon form or not. So we have three options here. Option 1 is not in echelon form. Option 2 is in echelon form, but it is not reduced. Option 3 is in reduced echelon form. So what can you guys tell me about matrix A? Is it option? So not in echelon form. Who is not in echelon form? Not in echelon form, right? So A is not in echelon form. Exactly right. Because you can check this, right? The leading one, it spoils. All right. How about B? Look at that. It should have been a 1. It's not. Not in echelon form. C, all zeros. Ones are looking good. Staircase is satisfying. C, which form is it in? I'm going to say C is in reduced echelon form, because it is already echelon, but the one, wherever the ones are there, you have no the other two entries in that particular column are, so this is my leading one here, and there is a leading one here. All zeros are at the bottom, and I'm following a staircase. So that tells me that it is in echelon form. Now I need to check for the special case. Is it reduced or not? Now, to check whether it is reduced or not, I look at the other entries in that column. Both zeros here, both zeros here. So the leading ones are the only non-zero elements in that particular column. So C is in reduced echelon form. How about D? What can you guys tell me? Echelon form. Leading one, good. Staircase is good. Yes. Because of this 3, it will not be reduced, right? So it is in echelon form, but it is not reduced. That's D here. All right. How about E? Reduced echelon form. Good. F. There's a 1 at the bottom. Not in echelon form. Yes. G. It is in reduced echelon form. What about H? Reduced echelon form. You guys agree with these things? All right. Leading one, yeah, leading one. Okay, nothing. Good. All right. So let's stop over here. YF. Oh, F. All, you need to have the 0 row at the bottom, right? At the bottom of the matrix should have zeros. The first condition was not met. You see it? All right. So I'm going to stop the recording over here. And then I'll talk to you guys about something.